How about this? Peter, you're the,
That's good. I'll move around anyway.
okay. Okay, so, I understand I have 2 hours. 2 hours is not enough even to talk about part of it. So I'll kind of give an outline. And we'll see what we get around to. Now that I'm somewhere maybe into my 60s, grandfather, I have a little bit of different perspective on things. So, really sort of, I think the point is my debt to, let's say, number theory and algebraic geometry. And there'll be principles that anyone who does algebraic geometry, number theory will recognize. But you don't need to know any number theory. That's a good thing. You don't need to know any algebraic geometry, because we'll sort of do everything in terms of graphs. The Hanna Neumann conjecture is a conjecture in combinatorial group theory. I'll just call it the HNC. Somewhere in the 1950s. I could tell you what it actually is. When I ask my dad, my dad's a mathematician too. He always says, you first say what the conjecture says. I'll say what the conjecture says. I'll quickly pivot away from it completely. So the conjecture.
Dad's right.
Pardon?
Dad's right.
Yeah.
He's always right.
Okay, yeah, dad's always right. Okay, so the conjecture is the following. So if you have a free group F, and you have two subgroups of the free group, and the ranks are finite, then there's a conjecture about the intersection of the rank. So you have the rank of H intersection K. You have some bound. You have the rank of H. You have the rank of K. So the first one to prove any kind of equality like this was Hausen, who proved that if these are finite, then you can bound the rank of the intersection in terms of the ranks of the group. The Hanna Neumann conjecture. So shortly afterwards in the 50s, Hanna Neumann proved the following bound. That if you subtract 1 from each of the ranks, and we'll assume that the ranks are at least 0. So if this is, at least 1. So if these are, rank 0, we'll ignore. So this is less than or equal to 2 times the rank of H minus 1, rank of K minus 1.
Can you remind us the exact definition of that?
I can't, but Doron probably could. The rank is just a free group of finite, it's
Yeah, it's a set, the minimal set of you can.
yeah, the minimal set of generators.
The size of the minimal set of generators.
Yeah.
Is also the basis.
Yeah. So every subgroup of a free group has if it's a finite rank, it has a finite set of generators. And the minimal one, these are actually free groups in some finite generators. And it turns out that the intersection of any two that line a free group is also a finite rank.
You're also assuming that H and K are free?
No,
they're just subgroups, right? They're not free.
No, they are free by.
They are free by certain theorems. So there's a theorem that says that if F is a free group and you have a subgroup of a free group, then it must be free. Yeah. Can't have torsion. So the way I would like to write it is I would like to say that the reduced rank of a group is just the rank of the group minus one. And then the Hanna Neumann conjecture is that the reduced rank, the intersection, is less than or equal to the rank, the reduced rank of H times the reduced rank of K. She proved this inequality with a factor of 2, and the conjecture by Hanna Neumann in the mid-50s was that instead of a 2, you can actually put a 1. And this was just, it just in every single case that people knew, the constant here was always 1. And 1 you can't do any better than. But I'm not going to tell you about free groups. I'm going to tell you about problem and graph theory. So through the work of Stallings in the early 80s, he turned this into a graph theory problem. And I'll start with the graph theory problem. So the problem is this. So first of all, I want to say, what is a graph? So as I said, if you don't know any number theory, it's no problem. Don't know any algebraic geometry, it's no problem. Don't know what a graph is, I'll tell you what a graph is. It's not a big deal. Everyone who talks about a graph has different conventions. There are 5 or 6 different notions. People have different ideas. So here we'll talk about oriented graphs. So a graph has a set of vertices, set of edges, and it has heads map and a tails map. So it's a collection of 4 things. This is a set, it's called a set of vertices. This is the set of edges. And H and T are maps from the edge set to the vertex set. So H, G, and TG are maps from the edge set to the vertex set.
You got the directed.
Yeah, so that's the thing. A directed graph is defined the exact same way, but we're going to work with oriented graphs. And I'll tell you what the difference is. Okay, so that's right. It's the exact same definition. You won't really find the difference until we start talking about their properties. Okay, and H is called the heads map, and T is called the tails map. Okay, this part of the blackboard good with you guys on the ones there? Okay, so for example, when we talk about connected components of a graph, so we picture them as the usual way. So vertices are dots. Maybe this is V1, V2, V3. Edges are pictured this way, but this is an orientation. It's not a direction. So yeah, you can have self loops. You can have many self loops. This means that you can have 4 edges and 2 self loops. It's not multiple edges are not a problem. Self loops are not a problem. So the connected component, you take this graph. This side okay?
So you're not thinking of the set of edges as being a subset of pairs of vertices. You're just thinking that as a set, and the heads and the tails maps are telling us the relation, the incidence.
Yeah. So that's a good point. I mean, it's true. Let's see, where can I go? If I write down here, can you people in the back see? sort of, I mean, you tend to write, I'll start up here. So you tend to write, you know, if you have an edge, then the edge has a tail. And it has a head. And you tend to write the edge as an ordered pair. So this convention just means that you can have multiple edges. Okay, so what's the connected component of a graph? Let's say you have a graph that looks like this, maybe this. The connected components of a graph, the first thing you do is you erase every single arrow that you see. You don't care about the direction. Then you say that two vertices are equivalent if there's a walk from one to the other in the graph, meaning a sequence of vertices and edges. They're alternating to go from one to the other. So V1 is connected to V3, V1 is connected to V2, and V2 you can walk to V1 and V3. So if this were a directed graph to your question, and we just had an arrow like this, we couldn't really walk backwards. We shouldn't allow ourselves to walk backwards in this directed graph. But because we're just viewing this as a graph, most of our definitions will not care about the orientation, and in fact, it's really something we can walk back and forth. It's just a convenience, really. There is an eraser.
Oh, nice.
Do not
Oh, there
erase.
is one over there.
Oh, great. Yeah, you can take pictures if you want. You can stop me. It doesn't matter.
I'm just being like lazy and not taking notes.
No, that's good. That's good. It was supposed to be an iPad talk, but
He's gonna put the notes on that.
yeah.
Oh, he's gonna put the notes so that I don't need to take, I don't know.
We could take, it's special.
Then I can-
So
His face will remind you.
now we're gonna define a few graph theoretic notions, and I'll say what the Hanna Neumann conjecture is graph theoretically. So the first Betti number of a graph, well, the zeroth Betti number of a graph is just the number of connected components. So the zeroth Betti number of this graph is 1, 2, 3, yeah, 3. B1 is the number of independent cycles in the graph. It's also the minimum number of edges you need to create a forest. So minimum number of edges to delete to create a forest. So this graph has 1 cycle, 2 cycles, so the first Betti number would be 2.
What about that one? P5.
Oh, right, 3. I stand corrected. So B0 is 3 for here, and B1 is 3.
What is the definition of a forest when you can have multiple edges?
A forest just means that you have a disjoint union of trees. So
So
if a tree is
there
created-
can also be no multiple edges because then you wouldn't have a loop between two vertices.
Yeah,
Okay.
yeah, that's right, that's right. So if we were to add another edge here, that would create another cycle.
Okay.
So here you don't care about the orientation.
Right, so we don't care about the orientation, it doesn't matter. And the Euler characteristic of a graph is usually defined as the number of vertices minus the number of edges. And it's also always equal to the 0th Betti number minus the first Betti number. Now we're going to define a slight variant, which will make everything much more difficult. And what is that? So say G is connected. Then we define the first reduced Betty number. So the reduced Betty number is just the maximum of 0 and the Betty number minus 1. And this is not so important to the talk, but it'll just sort of make things, hopefully, make a little more sense. The reduced 0th Betty number is the number of connected components that are trees. So for example, here's a tree, one vertex, no edges. This is not a tree, this is not a tree, so the reduced Betty number here is 1. Zeroth Betty number is 1, yeah. And then from each connected component, I subtract 1. So here, there's no cycles, there's 1 cycle, there's 2 cycles. So the reduced first Betty number is just 1.
You didn't define the reduced first Betty number.
Right. So if it's not connected, so in general, the reduced first Betty number, or the ith Betty number, or even any Betty number is just of a graph, is the sum over the connected components, G prime of the graph of BI.
Another way to say it is that you omit, you erase all the trees. Minus all the characteristics.
Yeah, you can eliminate all the trees, and then you just look at the,
All the characteristics.
yeah. And, it turns out that, of course, this is the same as the difference between the reduced Betty numbers, the Euler characteristic. Each of these notions take a little while to get used to if you've never seen them before. So, stop me at any point. Before I worked on the Hanna Neumann conjecture, I assumed that the first Betty number was the interesting one. It's not. It's the reduced first Betty number that's really the interesting one. Okay. Now let's do things a little bit differently. So why are the zeros reduced Betty number in the first one more interesting? So the idea is if you take a covering map of graphs, these are the ones that have the right behavior. So if you have a graph G, and we don't really care about orientation, we could put them in. So a covering map is just a topological covering map when you think of this as a topological space. So let's say of degree 2, so for each vertex you have 2. So these will map to here, map to here, this maps to here, this maps to here. And then for each edge, you put in essentially a perfect matching. So maybe I'll put in a matching here, maybe this one I'll cross over here. Maybe there's a self loop, and the self loop could also open up into two multiple edges. But the idea is that when you look locally at each vertex, so I got something like this, then downstairs I should see the same thing locally. And locally means that I just look very near the vertex and I ignore the fact that some of these edges may be self-loops, some of them may not be. So this is called a covering map. I always have this problem. So Nattilineal calls this a lift. And he said we will use a lift because in covering means different things in discrete math. So, you know, the map H to G here, you can call it a two-lift, or you can call it a covering map in the topological sense. Of degree 2.
Wait, Borel once schooled me on the notion of covering that, so.
Pardon?
He was very unhappy about even the word covering. He said, cover. And he had some reason, I can't remember any. But I remember him complaining.
Yeah, I don't know. Most people think of graphs. I mean, those who think of it as a discrete thing, those who think of it as a geometric thing. Me, you know, that's my.
Can I complain about something
Sure,
to, as a
complain.
question?
Yeah.
So it looks like there you've got those two like like isolated vertices up there that are mapping to a vertex that has edges coming out of it. So like
Oh, sorry,
topologically speaking, this
I
wouldn't be
I haven't filled this out completely yet.
Oh, okay, so
So,
you
yeah,
would
yeah,
need
you're
that
right,
it's
you're right,
like an
you're right.
actual covering.
So I need a one to go here for this guy, and for this guy, I need one to go there.
Okay,
Are you? Yeah.
I'm happier now.
Now I think it's a bona fide covering, so I've got two fibers over each vertex, each edge, 1, 2, 3, 4.
yeah, you do have,
Yeah,
oh,
okay.
never mind.
Okay. On the iPad, I used different colors for its different vertices and edges. Here, it looked a lot nicer. I appreciate your patience. Okay, so this is
There are some colors over there, in case you want.
if I try to use them, okay, that's a good idea. So this is call this a covering map of degree 2. So theorem is that if you have say G and H are connected graphs, and orientation, we don't really care, you know. These are connected graphs, and they're finite, let's say. Then for some, say, natural number P, this is really a D to 1 covering map everywhere. Comes to graphs, can't move this aside. Pi from H to G. It's a covering map. Well, call it a lift. Call it a lift. Then the map pi is D to 1. Meaning that if it's 2 to 1 over here, then on this edge locally, I have to see 2 copies up there. And then on this vertex, I have to see 2 vertices there. And so if it's 2 to 1 in any of the fibers and it's connected, it's got to be 2 to 1 everywhere. Some natural number D. And the other thing is, if you look at the automorphisms of H that respect this structure of pi, then its size is in most D. So an automorphism that respects the structure pi just means that in each vertex and edge fiber, you permute things around and it's really a map of graphs.
If you have D different copies, like is it D factorial? If you have just D disjoint copies of your.
Right, so it's crucial that they be connected, yeah, so
both
that's,
copies,
yeah,
okay.
so the remark is that if H is just D vertices and G is a single vertex, and you take the only map you can, so there's, the fiber size. Fiber of the vertex V is size 4. Number of automorphisms is 4 factorial. So it has to be connected. And the way you prove this is the lifting property of paths. Lifting is a mathematical term, not a graph theory term. So if you don't want to confuse a lift of a path and a lift, you would say covering map. So but don't tell Nati that I said this.
What if H is a complete graph there? How does that work?
Yeah, so if H is a complete graph. So where are we?
Wait, can I take a photo before you erase it? Sorry.
Oh, yeah, all right.
I should have done that earlier. Okay, thank you. Sorry. Yeah, I'm good.
So if H is a complete graph. So H, let's say, is a complete graph. So what is the complete graph? Well, if we have oriented graphs, yeah, let's just this kind of complete graph. Then it's locally degree 2, so there's actually a map, a unique covering map to the graph as a single vertex and a loop. And if we add an orientation here, then we would naturally sort of add some sort of orientation here. So this is a degree 3 covering map.
The number of automorphisms depends on the orientation then?
So I will now erase the arrows again. Yeah, so
Or is it not 6? I don't know.
right. So the problem is that this, without the orientation, has non-trivial automorphisms in the usual sense of a graph. Because you can take this edge. A graph truly is just a directed graph whose directed edges come in pairs, and this admits an automorphism. So to your point, yeah, well, let's keep the orientations in. Any other questions?
Still, can you explain why it's less than at most D, like,
Yeah. Oh, yeah. At most D. So that's also the lifting property.
Mhm.
If I have a map from here, let's say I start by looking at an automorphism. And I take, well, for degree 2, there's only one non-trivial automorphism, which changes the fibers. And I say, well, what's going to happen on this? So if this vertex is mapping here, I take a path from here to here. I push it down. Then I lift it here to there, and then I can sort of see that has to happen. And it doesn't matter, if there's, an extra degree and everything, it doesn't really matter. Once I fix a map from a single vertex to anything else in the fiber, it's uniquely determined.
it's forcing all the other elements in the fiber?
Every element in the entire graph, if it's connected, is forced.
Because it
Yeah.
propagates, what it can come back later.
Yeah.
I have a question though.
Mhm.
So you're treating multiple edges as labeled in this,
Yeah, so treating multiple edges is labeled.
So labeled by the edge they. send,
Yeah, I mean,
right?
a
Each edge
graph.
projects to an edge below, so You can think of the edges below as the
Oh,
labeling of
sorry,
the.
like we're treating this map not just as map of vertices, it also maps.
Oh, yeah. The graphs map
So,
vertices to vertices, edges to edges, if it's oriented, preserving orientation and respecting the heads and tails maps. Some point I should say what the Hanna Neumann conjecture is. Yeah. But well, let's go with the flow a little bit, okay? So this is most D. So if there are exactly D, we say that the map is a Galois cover. So if we have covering map to G that's D to 1 covering map Orland, and these are both connected. Well, I mean, then if the automorphism group of H is actually equal to D, we say that the map pi from H to G is Galois. And one of the facts that we will use from number theory is that there always exists Galois extensions. So we get some intuition.
For every G and every D, there exists a Galois extension.
So the normal extension. So let's say H and G be connected just for simplicity. Connected oriented graphs. And pi from H to G is a D to 1 covering map. Then there exists a covering of, then there exists you have H to G, this is pi, you have an H prime that maps to H and then down to G, where this is a covering map. This is a covering map, and in fact, it's not only covering map, it's Galois.
What's the degree?
The degree, that's the embarrassing part. The degree here is at most d factorial. And the group, I don't know. So this is something I was really excited about. Audrey Terrasse is also very excited about this. It was discovered maybe 10 or 15 years before we discovered it, but this is kind of a really neat theorem. However, Harold Stark also was very excited about this. Papers about zeta functions of graphs and so on. However, it had 0 applications, I claim, before my proof of the Hanna Neumann conjecture. Now it has.
They did have some.
I don't understand the definition. So suppose H equals G, and we just take the identity map.
That's
the
right.
Covering map, then this seems to be not true, right?
If H equals G, so for G to G,
Just take the identity.
then just take G to G to G.
Uh-huh.
It's automatically Galois. Degree 1 is always Galois. Degree 2 is always Galois.
But then it says that every graph has at most one automorphism. Has at most one automorphism. Right, if,
I mean, this could be a Galois map. If this is already Galois, then H prime can be H, and this is the identity.
Or every graph has only one automorphism respecting the identity of to itself.
oh, I see, there is a constraint on the automorphisms.
Yeah.
I see,
The little pie
Yeah,
has
the
to be
little
fine.
pi, I mean, if you have a different pi, it's a different automorphism group. It's different
Okay.
thing, basically. Okay.
They were trying to understand the zeros of the zeta function, so they did have some interesting examples, so.
Yeah, they had interesting examples, but to actually use this in a proof of a theorem, but at least, maybe there are more applications.
So automorphisms of H that respect pi, they have to act on each of the little clouds separately. They cannot mix them. Understand what it means.
I'm just saying, there exists an H prime that maps to H and G.
I'm looking at the definition of automorphisms that respect pi.
Oh, okay,
Just
oh,
understand what
yeah,
it means.
So
Means
that
you
just
have to act
means,
on each cloud separately.
well, it's just any map from H to H
Yeah,
that respects
each fiber.
the fibers. This is the formal definition of the automorphism group. So it's automorphisms mu of H such that it respects that.
So it has to act on each.
It has to, that's right, it has to, on each fiber, it's basically a permutation of each
Permutation
fiber.
on each fiber. So it
Yeah,
has nothing
yeah.
to do with automorphisms of G.
It has nothing to do with automorphism of G, that's right.
Not that it projects down to them.
And as usual, I'm running out of time. I thought maybe the first 45 minutes, I'd talk a little bit about the conjecture and phase change and so on. But this is a nice enough story too. I should say something about sheaves at some point, but okay. And I mean, the proof is just the usual proof. So if you have, V and you have V1, V2, V3, and this has, let's say it has a single vertex and two colors. And maybe the map is like this, but V loops to itself and V1 and V2 under this other directed edge exchanges this way.
What's the white arrows and what's the red ones?
So these are two edges, but I'm choosing two. So this is a graph H.
Oh, there's a graph H and there's a graph G.
Yeah, sorry,
Okay,
yeah.
H is like a three.
H is a
cover
three
of-
lift, yeah.
Three
Three lift, cover of degree three.
Okay,
We have a three lift. For
okay.
example, here, there's no way this is Galois because V3 has a red edge to itself, but V1 and V2 are interchanged.
So why does that mean it's not Galois?
It's not Galois because there's no morphism from V3 to V2 that can respect pi. Because if you follow V3 with an edge downstairs, you come back to yourself. But if you follow V2 with a red edge, you get to V1.
Yeah, I still don't see how does that mean? So to see if it's Galois or not, what do I need to check?
But you have three of them. But you can pass from it's transitive on the vertices.
Yeah, there's a transitive
And this
group
just
acting
has
on the
no,
vertices.
this has no automorphism stuff. It's H.
Okay.
There's just no automorphism.
So John,
Okay, in
maybe
particular, H is
explicitly,
just disconnected.
like you need to say that not only the size of the D, but actually the automorphism is determined by like to which vertex you're sending some given vertex.
Yeah, so in any graph, if the fiber is of degree 3, then as soon as I said V1 must go to V3, it determines the entire automorphism of every vertex and every edge.
Yeah. Just the fact that H is disconnected is also,
Well, there's a path from V1 to V2 and V2 to V3 and V3 to, so this is a
it's not
connected.
from V2 to V3, how is that? Oh, what's out there?
This is an
The white
edge.
and the red arrows.
I
What is
see.
the meaning of
Yeah,
the white and the red
I didn't
arrows?
look at the white arrows.
Yeah. Yeah, so I'm trying to transition to red and white arrows for a reason.
Okay, I see now. So it is connected, but still it's not a good one.
It's not Galois. So what do? You write V1, V2, V3, you write all permutations of the vertices, V3, V2, V2, V1, V3, V2, V3, V1, V3, V1, V2, 3, V2, V1. And now you say, well, I mean, this is really a permutation that goes V1 to V2, V2 to V3, V3 to V1. So V1 goes to V2, V2 to V3, V3 to V1. So I find the permutation down here that represents that. So it's V2, V3, V1, and I put an arrow here. And then you keep going. V2, V3, V1, V3, V1, V2. Back here, and then this will go V1 to V3 like this, and then everything is symmetric. So this is a covering. If you have a subgroup of a group of finite index, then there's also a normal subgroup beyond that, and that's the same proof, basically.
So for H prime to H is just taking the first one.
Yeah, that's right. So this is H prime. And now we can take, the projection of the first one, for example. Or the second one if you really want to, or the third one, doesn't matter. So this is the so-called normal extension theorem. If you, like me, were asleep in your algebra class, you remember about cube root of 2 being a non-Galois extension of Q, it's no problem. Here is a non-Galois extension. Here is a Galois version of it. Really using the fact that you can view this as a symmetric group on these three things, and that's done. Degree 2 is obviously, there's always just something that flips two vertices. Degree 3 and higher doesn't have to be Galois. Okay. So now, what else should we say? Let's talk about the Betty numbers again. Yeah. So if you have map H to G and it's a D to 1 covering map, then the number of vertices of H, it's clearly just D times number of vertices of G, because in each vertex you have some D things in the fiber. Similarly, the number of edges in the covering graph lift is D times that. The other characteristic is just the size of V minus.
Should be E of H, E of G.
Oh, thanks, yeah. E of G. The Euler characteristic is just the vertices minus the edges. So therefore, the Euler characteristic is D times, Euler characteristic of H is D times the Euler characteristic of G. And now the claim is the first reduced Betty number and the 0th reduced Betti number also multiply in this fashion. So from the point of view of covering maps, it's the reduced Betti numbers that are kind of the well-behaved things. Oh,
No, I already did, thank you.
okay, okay. So,
I mean, topologically, you should, it's because it's one dimensional. I mean, if in higher dimensions, Betti numbers don't help.
yeah, I mean, this is,
They used to call them irregularities because they behave so badly at the cones.
I see. Okay. So. Let me talk about one more important concept, which is sometimes called an immersion, I call it, or an étale map. So if you have so you say that a map H to G is maybe étale or immersion. I'm not going to tell you what's an open immersion or closed immersion because that's going to be embarrassing for me. So it means if there's a map from H to a larger graph. So you can say this is an inclusion or a subgraph. And then a map to G where this is a covering map such that the map you get here is really pi. So a covering map is étale. The inclusion of a subgraph into a graph is étale. And étale really means anything that's an inclusion followed by a covering. So for example, let's say that we look at a very simple graph here, B, which has a single vertex and two oriented edges. Say one white, one red. Covering of degree 4 might look like maybe this goes to here, to here, to here. You have a self loop. And here you go back and forth and back and forth. So if you take this and you take any subgraph of that, that's by definition étale. So we take the same graph, but maybe we erase some of the white arrows. So maybe you have this arrow, but not the other ones, this, and maybe you have this and this, but you have only an arrow here. So that's what I'd call an étale map. In other words, if you look at it as a map here, for every node, you see at most one white arrow coming out, at most one white arrow coming in, at most one red arrow leaving it, and at most one red arrow coming in. So there's a theorem called Hall's theorem. It is not the Hall's theorem that I learned in the beginning. It just says if you have any map that's locally into, then you can extend it to a map that's actually a covering map. It goes down here. And combinatorially, that's very, very easy. If you wanted, if I
Is it the
erased,
same Philip Paul?
no, a different one, I think, yeah. if I erased these arrows now and I wanted to fill them in, so I have this, well, what can I do? I mean, these each have one coming in and one going out. This has one going in, but nothing going out. This has one going out, but not going in, so I can just add this. And similarly, this guy is full already, this guy has nothing coming in, nothing out. So there's a bunch of ways I could say, okay, maybe this one goes out to here, and then I get a self loop here. But however many are missing a head, the same number are missing a tail, so you can take this.
You might not find a connected graph, right?
That's right, it may not be connected. So if it's not connected, we kind of have to change the definition a little bit. We have to say Galois really means you have a transitive group acting on the phi1, simply transitively. So if you have 4 disconnected points and you have a single point here, you have to choose some group on the 4 elements so that you have a simply transitive graph. Okay. So now the Hanna Neumann conjecture, actually a strengthened form due to Walter Neumann, who is a son of Hanna Neumann. So you have to start being more precise about these things. And in the graph theoretics setting,
Son of Hanna Neumann Conjecture.
son, yeah, that works too.
Walter was the one who lived here. He passed away very recently.
Yeah.
He lived in Princeton.
So in graph theoretic terms, and this is a sort of dictionary due to Stallings, is the following. So let's say you have 2 étale maps to B. So say, we'll say a map to B is the same thing as coloring some of the edges white and some of the edges red. So say you have, I mean, you could say it a number of ways, but you say, a bicolored.
Okay, so finally, the reason you had white and red is emerged.
Yeah.
So only 2 colors?
Yeah, only 2 colors. My methods don't work if you have 3 colors. So Warren Dix pointed this out. Completely falls apart with 3 colors. But if you can prove it for 2 colors, you can prove it for 3 colors because the free group on 2 generators, the free group on 3 generators lives inside the free group of 2 generators. So let's say a bicolored graph is just a map on the graph X to B, where this is going to be our sort of our favorite base graph. Like this. We'll say that, moreover, we'll say that it's étale. So an étale bicolored graph, if this map here, pi is étale. When you have 2 bicolored graphs, there's a so-called bicolored product. So if X is a bicolored graph and say Y is bicolored, so you have maybe, I don't know, some edges here an edge here. Maybe you have a red edge here, maybe a red edge here, and so on. There's a natural product. And usually there's some kind of abbreviation for this product, which is x, I'll say x star y. What you do is you take the product of the vertices. So the vertex set of this x star y is just the Cartesian product of the vertices of x and the vertices of y. To each white arrow, we make the product of the white edges. So we take, let's see. You guys in the back, can you see this if I write here? Sort of, more or less. Okay, so the white edges these are just the white edges of x plus the white edges of y. So I've got an edge, two edges, and one. I should have two edges in the product. And if the white edge from here goes from here to here, and then this goes from here to here, I make this right there. And similarly, this one, and for the white, for the red, I have 1 and 1. So there's a single red edge here that's a self loop. And in this direction, it goes back over these two vertices. So I would basically get a single red edge like this. This red edge does what y does here, and it does what x does here, which is stay in the fiber.
So the reds are also Cartesian.
The reds, and the same thing
They
for
just
the
don't
reds.
talk to the white.
Yeah. White one's red.
And it's not Cartesian, because you move both coordinates at the same.
Yeah, that's what he means by Cartesian.
Yeah, it's like the tensor product
Yeah.
in terms of the adjacency matrix.
So you basically tensor the red separately, the white separately.
Yeah.
I missed why we can work just with two.
This will not be explained. You have to read Stalling's paper, and then you have to realize that the free group on 3 elements is, this is the setting of the Hanna Neumann conjecture as Stallings formulated it.
It should not be obvious to us why two
It's
generators
not,
are enough.
it's not at all obvious. It's not even obvious why this is interesting, right? Why this particular graph is interesting.
So what is the, I'm sorry, so maybe I
Okay.
missed something. So what is the formulation of the conjecture now? And
We haven't yet
we haven't
formulated
said
it. We're about to formulate it after an hour's worth of,
Okay, by the way, you don't need to take a break, but if you want to take one.
I can take a, you know. I mean, I probably don't need one. You probably need one more than I do, so. Anyway. Probably gonna have to start summarizing things, so. This kind of product is actually an example of the fiber product. So, more generally. So if you have any graph B and any x, any y, and you have maps from both to base, there's a graph you can construct which is called the fiber product of x and y. And it maps to x and y, and if you look at the category of all objects that map to this diagram, this is the terminal object in the category, the terminal object. So this really is just a fiber product. the way the fiber product works is that you look at the fibers here, you look at the fibers over each edge and each vertex, and you take the products. And then you create a graph out of it. This is called the fiber product. So I'll state the Hanna Neumann conjecture. Maybe I'll outline sort of the first step, which I spent enough time on. So the strengthened Hanna Neumann conjecture states the following. So let B be the base of single vertex two self loops. Let X and Y be two étale maps. Or if you want étale bicolored graphs, look at the fiber product, which is really what we call the bicolored product. Then, and B here is single vertex, a white loop, and a red loop. Then the first reduced Betty number of X star Y, the bicolored product, which is the same thing as the fiber product, is less than or equal to the reduced first Betty number of X times the reduced first Betty number of Y.
So this was conjectured by Stallings. And
This, I mean, the Hanna Neumann conjecture was with the reduced ranks.
did he have a topological application in mind, or was he just trying to solve this?
Stallings, you know, I don't know all aspects of the paper, quite frankly, but he
No, but this is
basically.
the conjecture of Neumann, of
Yeah,
Walter
this
Neumann. no?
is Hanna Neumann's conjecture, but this is Stallings' way of taking statements on free groups and
Yeah.
converting it to graph theory.
But he was studying free groups. Rather than, I mean, he
Johan
did a
can
lot on
probably
Friedman.
tell you more than he was, you know, there's all these things like, you know, Yara's work in the sixties.
Yeah, that I-
Sam pointed out, you're basically doing
Yeah.
graph theory, even though you're talking about p-adic Lie groups. So there's all kinds of things in combinatorial group theory, even things that don't look so combinatorial that turn out just to be combinatorics. So Stallings' contribution was to state the Hanna Neumann conjecture in these terms. And then Walter Neumann had the strengthened conjecture, which amounts to this.
So can you reformulate this back as a group theoretic statement?
You can. So the Hanna Neumann's conjecture is that any connected component of this satisfies the inequality. And you can talk about double cosets of H and K and reformulate it as such.
Just on the basis of pattern matching, in the Hanna Neumann conjecture, you had the intersection of two things on the left-hand side, which are smaller than each of them. But here you have something larger than each of these two X and Y's on the right hand. So it seems something has been inverted in this conclusion, right?
No, the right hand side is the same.
The right hand side is the same, but the left hand side.
Yeah, just,
Okay.
here you go over all connected components in the original one, you just pick one.
So let
Component
me,
in the
X
cover.
star Y has more vertices, more edges than X and Y individually, right? Because it's a problem.
right,
H
but
intersected with G is a smaller object than both H and G. So somewhere there was some
that's in
reversal going on.
Stallings' translation of what free groups are to what graphs are.
So as the graph is the constraints, the relations, there are more relations in the intersection.
Well, let me state it slightly differently. So here's the first result, is that the strengthened Hanna Neumann conjecture is equivalent to the strengthened Hanna Neumann conjecture restricted to the following case. G is a Cayley graph on two generators, G1 and G2. Cayley graph on a group G with two generators, we can say what it is, but it basically gives you a bicolored graph. And where X and Y are subgraphs of G. This is the first result.
Are these finite or not?
Subgroups or?
These are, so this is a graph. This is a bicolored graph. These are subgraphs. These are subgraphs.
Pete is asking you, is this a finite group? Or is this
Right.
a
Oh,
discrete group?
finite.
Finite.
Is finite. And these are subgraphs. So you have a Cayley graph G. Maybe it looks like this. Maybe it has self loops red that go back to themselves. So this is on the numbers modulo 3. The first generator is 1, the red generator is 0. Therefore, you have the group in which the Cayley graph is formed acts on the graph. And then the claim is that, in fact, the claim is that X star Y is the same as disjoint copies over all the group of X intersect GY. So if this star, it looks like some big product, it's in essentially it's just a bunch of disjoint copies of taking one graph and twisting it by Y. So this is the conjecture. This is the first reduction. And with all the stuff we've built up, we can pretty much explain why this happens. So this might be a good time. Let's take a few minutes break if you want. Back in 5 minutes.
You're saying this star product looks big because it has a lot of vertices, but actually it has very small connected components.
That's
So
right,
it's
that's
very
right,
small.
that's right, that's right.
Question, how should I understand GY as a graph?
GY, okay, so, the. So if you have a graph like, in this case. So you have, let's say this is Y.
Okay.
Then I haven't defined the Cayley graph, but if you're good at that, the Cayley graph is just,
I think after this we'll go.
say something like this. Then, so the vertex set is just G itself, and the edges are, you connect every G to G1 times G, and every G to G2 times G. And that's the, notation. So then, this, example. So if G is equal to the integers log 3, okay, G1 is 1, G2 is 0. So then basically the symmetries sort of twist, and therefore this is twisted. So Y is single loop here, this is Y. Then one,
I see,
Acting.
we relabeled the vertices.
that's right.
I see, okay.
Really, in a sense, you're just twisting this, but you still want to keep the labels the same.
I see.
1 times Y and 2 times Y. Or, it's an abelian group, I'm tempted to write plus instead of 1 plus Y, 2 plus Y. But you do want to think of the underlying graph as staying the same, and then you just have these symmetries. So if this is, vertex V, then this should be vertex V, but this should be vertex V, and this should be vertex V. And if this is vertex W, then this should be vertex W, and W, and W. So these are 3 different graphs, 3 different subgraphs, but they have the symmetries.
Stallings actually himself translated the Hanna Neumann conjecture, or it just comes from his machinery?
It comes from his machinery,
Right.
I'd say.
Because I've seen Stallings' machinery before, but
Yeah.
I don't know if he himself-
I don't know if he has it in the paper.
No.
If Not.
The back one.
I was very helpful.
I'm not familiar with that, that's a whole.
Learned this from the Rubenstein. Yeah, I mean,
Oh.
Stallings has this whole technology of turning group theoretic problems, free group into graph theory,
Yeah.
4 graphs.
Yeah,
And
yeah.
this thing at the bottom
stuff.
here of those 2, this bouquet of 2 loops is just the free group generated.
Right.
I'm glad you asked the question, because now we have a picture of what this is actually saying.
If these some other graph, something like this holds within 2 or something like that, or?
That's a good question. So it should hold with like a bouquet of 3 self loops. And it does, but that's because the free group on 3 generators lies in the free group on 2 generators.
Or if it's some arbitrary graph, is something like this with some constant would work, or?
Yeah, so that would be called the rank intersection constant of B. So for any graph, you could say, what's the best constant here? And there's a series of problems.
It has to be like a finite constant.
So the reason why Hanna Neumann could prove the constant 2 is because they're just 2 edges. So this is a finite graph with, I think, m edges, and the constant would be at worst m. It may not be exactly true, like if it's disconnected or something,
If you have 3 graphs mapping to B.
Oh, 3 graphs. I mean, you could take if you want threefold product, then it would
You would get this.
It would hold, yeah.
Of the column.
Yeah. That's probably what we won't talk about, but it's I can just outline the proof of this and then maybe we can talk about sheaves for a bit.
Okay.
Or not. Doesn't matter to me.
Like a great one, I've never encountered the name before.
Hanna Neumann?
Yeah.
She was born around 1910s or so.
But does she have a whole series of results in group?
Well, there's
there's
the, what is it called? The Higgs, Higson's Neumann construction, and so she has other results. She has a famous construction with her spouse.
Just,
Two Neumanns.
Not the Walter.
Not Walter Neumann. No. That's the spouse of Hanna Neumann.
There's also group.
I don't know the scope of his work, but it included this.
By the way, this picture, what?
This, okay, maybe I'll call Glenn if you want to, okay. So in the break, there was a question, what does this really look like? So the example is that if you have a graph Y that's a subgraph of a Cayley graph. So I didn't formally write out the definition of a Cayley graph, but a Cayley graph on a group G with two elements G1 and G2 is the graph with vertex set G, and the edge sets connect each element G to G1 times G and G2 times G. If you really want, you can put the multiplication on the other side. So in the case that I'm picturing here, we have an abelian group. So we have the group of order 3. The first generator adds 1. The second generator adds nothing. And so you get the Cayley graph of G with G1 and G2 is the white edges add 1. This is, really 0, 1, and 2 modulo 3. And the red edges are just the translates of a subgraph, say like this, where you throw away, you keep this red self-group and throw away the other two. The group therefore acts on this, these images. We're multiplying by here, probably the group needs to act on the right. But I'll ignore that and just write GY. Then when you take the graph Y, the translates of Y, when you add 1 and add 2 modulo 3, simply spin the graph around. So this is the picture to have in mind. Okay.
This equality of just definition chasing.
This equality?
Yeah. Like
So that's a good question. So now I will just state a few facts from, algebraic geometry. And it's, the short answer is yes, you can get it by just definition chasing. But there's some standard facts. For example, if H to G is Galois, then if you look at H fiber product with G, H, you get a bunch of disjoint copies of H. This is supposedly a way of proving Hilbert theorem 90. I've never gone over the details myself, but when I saw this formula, I said, wow, that's, a great formula. And the proof is very easy. I mean, if you have, say, this graph,
What does it mean, product of a G in Galois?
So it's a.
it means that these are G copies of H, but they lie in a very specific way. So if you take the product of these two graphs, these are covers of the graph with a single edge. And if you write them out and you see what the product does. So from here, we advance 1 in the right direction and up. So we would have this arrow. And continuing from here, we would move to this arrow, and then we move back to here. So this is sort of the diagonal. But then if you shift by 1, if you're here, you're still adding 1. And then adding 1, which takes you here. And then you add 1, which takes you here, which goes back to there. So the vertex set of this graph is just, it's just, you can think of it as you take any vertex of H and you multiply by G. So V is the vertex, it's really an element of G, and G is the symmetry of the graph. And so you get that in a Galois map, the fiber product breaks apart like this. And the other thing about the fiber product is that it preserves local properties under base change.
But Joe, before you erase this,
Oh, yeah?
you said you would, did you prove it or? Are you intending to prove this or you said you could?
I'm gonna outline a proof and then say that I'm not gonna do any more unless you really want me to, and I'll start talking about sheaves. So let me leave this here. So there's one more notion, which is if you have a general fiber product, not over a base, but not over this particular base, but if you have any, let's say, graph B, any graph X, any Y, and you form the fiber product, then if this map is F, and this is G, and this is F prime, and this is G prime, then any local property that holds of F also holds of F prime. So F has blah, blah, and blah, blah is some sort of local property. Then F prime 2. And if you've never worked with this before, it might seem weird, and you might say, why do you want this at all? If you're trying to solve a polynomial equation over the reals, you might be unhappy that there are some linear factors and some quadratic factors that don't factor, but if you extend to the complex numbers, everything behaves nicely. So this sort of fiber product just occurs in number theory and in algebraic geometry all the time. And the same principle holds there. And I didn't come up with this idea myself and then see that the algebraic geometers figured it out. I stole it from the algebraic geometers. So,
Can you give an example for?
Yeah.
In graphs. In these graphs.
Yeah, so let's say, I'll give you some simple examples. So let's say you have a map X to B, and on the vertices, this is 5 to 1. On the edges, maybe it's 4 to 1. But it's exactly 5 to 1 on the vertex. I'm not making any assumptions here. Then if I take any y and I take the fiber product, then this is also 5 to 1 on the vertices. And the reason is that if B has a few vertices and X has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, maybe some edges, be mapped this way, then every vertex fiber here has 5 copies. But the vertex set of this is just the Cartesian, just the fiber product of the vertex set.
In one sense, this doesn't have to be a local property, right? And those vertices, these 5 vertices may be very far apart from the graph.
Right. So it's local in the sense that when you consider a map from here to here, what's happening is local in the base.
In the base, not in
Yeah.
the, not upstairs.
Not necessarily upstairs.
But if you look at the edges, it's no longer true, right? Because some of the edges in the
Yeah, I mean,
fiber product no longer behave as nicely.
yeah, I mean, I could have, 3 edges here, and I could have no edges here. That's still a map. It doesn't have to satisfy any condition at all. It's just any morphism of graphs. 5 to 1 there, 5 to 1 up here. If I say there's twice as many vertices here as here, I could have a whole bunch mapping to a single vertex and almost none mapping to another, and that wouldn't be preserved. Here's another property, real property. Let's say it's a covering map. Or, a lift, if you, in deference to Nati, we'll call it a lift. This is also a covering map. Or lift. If this is Galois, this is Galois. If this is an inclusion, this is an inclusion. Anything that you can define locally satisfies this.
Why is the counted as a local?
Yeah, because I mean, the automorphism is global, but on the fibers, it's local. So I've talked for an hour and a half and I haven't said a single thing about sheaf theory. This I stole from algebraic geometry. This I stole from algebraic geometry. It's an SGA 4.5. It's a proof of Hilbert theorem 90. And the Galois covering stuff, everyone who encountered it stole it from number theory. So this is our debt. This is our first debt to number theory and algebraic geometry. So how do we restrict to this case? Well, once you get used to what doing these things and what they mean, it is just a big hairy diagram. Kind of looks like this. You have, this is a particular base graph, which is one vertex and one edge. These are étales. So this can be completed to a covering map. This can be completed to a covering map. So I include y and x into slightly larger graphs, which are coverings. Now I take fiber product. Because of base exchange, these are covering. This is a covering. Therefore, there is a Galois covering. It's Galois to here, and it's also Galois all the way down here. And it's Galois to any intermediate thing as well. And now you just march away. I mean, these are inclusions as subgraphs. So now you can take the fiber product here. So this is a covering, so this is a covering, this is an inclusion. Fiber product with this and this.
Now use the theorem about this local property.
Yeah. So all of this, you know, when you build like this, it builds you a Galois cover of B. A Galois cover of B is really just a Cayley graph. This being Galois really means it's a Cayley graph. And then you take fiber products and move all the way up. And you get subgraph and a subgraph, basically because the arrows down here were subgraphs. It helps to do a few examples to make sure that all this stuff works, but that's the way it works.
So the point is, if you prove it for covering maps of X and Y.
Yeah.
All this equality is.
Yeah.
Beautiful.
That's true.
If it's true for the base graph, even if it's true for the covers.
Yeah. So if you have this fiber product is less than even some constant if you want, times the reduced Betti number of X times the reduced Betti number of Y, and X prime to X is a covering, then it's also true that same holds X reduced Betti number of X, reduced Betti number of Y, but now you can put the prime here and here. And this is again proven by some sort of diagram. You take X, you have X, fiber product Y, you take X prime, you have X prime, fiber product in X of X, fiber product Y over B. And now this is times X, this is divided by X, this goes away, and this is this. And right. This is a covering map, so this is a covering map. So when you compare this to this, that means you just get the same multiple here and here as you do here and here. So this is part of my debt to algebraic geometry. The next part is to see how to use sheaf theory to settle this case. When I discovered this, I thought this was really like almost solving the problem. Then a few weeks later, I thought, no, it's not doing almost anything. But it is the way my proof works. So it is doing something, but it doesn't completely solve your problem. But it's an important reduction. Okay. Do people have, if you have more questions about this part, I'm happy to talk about it. But I did put sheaf theory in the title, and that's my other debt to algebraic geometry. So I'm happy to talk about sheaf theory or answer any questions. Any questions?
So what do you do with sheaves?
What do I do with sheaves? Okay, glad you asked. So now, oh no, I erased this nice example. So now we have X intersect G, Y. We have some topological invariant like the reduced Betty number for summing over G. And we want to compare it to B1X, B1 reduced Y. So
Can you remind us where this joint union property came from? That's just, that was a fact, that was one of those facts you wrote down from H.
yeah,
H and H.
that falls from the fact that if X and Y are subgroups of graph G, and G to B is Galois, or in other words, a Cayley graph, then G tensored with B is just the same thing as some number of copies, disjoint copies of G, where G is acting in Galois. And specifically, you know, the vertex set of the fiber product of G with itself over B is the same thing as you take a set of all vertices and you multiply them by an element of G. So here, B is a vertex of G, which is the same thing as the group, and little g is an element of the group. But morally, you think of them as different. So there's a thing and G times the thing in the diagonal here, pulls apart. And the same with the edges of every color as well. So the fact that this is a disjoint union really means that what you have when you look at the product of X tensored with fiber product with Y over B is really, you're looking at, say, X vertices, you're looking at Y vertices times G.
You're viewing X times Y as a subgraph of this G times G, and then it just,
Yeah.
the thing just kind of. falls
Yeah,
apart.
yeah, that's the other point. So if
The
X,
point of this theorem, this theorem, what it's giving you is that you have this Galois, that it is Galois, so that you can
Yeah.
apply the statement.
Yeah.
Is that what you think about it?
yeah. So I mean, as you say, if X and Y are just subgraphs of some graph, you know, H, then when you take the fiber product of X and Y, it's the same thing as just X intersect Y as subgraphs. Of H. Because H is some kind of graph here. And X is some kind of subgraph. And so is Y. And you just, over each vertex and edge, you either have fiber of size 0 or size 1. And the only thing that survives are fibers of size 1 here and here. So this is just intersection. When I talk about Hanna Neumann conjecture, I usually skip all of this and I just say, let's start here. But any other questions? Before we proceed to Dohan's questions about sheaves. Okay, so now the proof comes in 2 steps. So the proof is really 2 steps. First, we prove the conjecture when X is the entire graph. 2, we get an immediate consequence. There is a slight catch. When I say we prove this conjecture when X is G, I don't mean we actually prove these easy way. You just, this is not what we're gonna do for one. What you can say is, well, what happens when X is G? Well, if X is G, if X is the whole graph, then what we really want to know is we're taking the sum over all group elements of the reduced Betty number of G intersect GY. G is the whole graph, so this is just GY. And the first Betty number of the graph will be exactly this will be exactly the order of the group. And this is the reduced Betty number of Y.
The equality.
Even equality is true. And this shows that the constant can't be improved. So if you have, a graph like this, then it has a single cycle, so its reduced Betty number is 0. And then if you add G more loops, you get that the first Betty number of this reduced is 3, which is the size of the group of order 3 acting on it. So this is easy. Translating the group doesn't do anything. You have basically the size of G here. You have the first Betty number of G times Y, which by symmetry is this, and you get that. Combinatorial group theorists will tell you this is trivial. What do you mean we immediately conclude this? Well, we proved this the hard way. One is done the hard way, the sheaf theoretic way. In fact, we're going to prove a slightly stronger conjecture on sheaves. So I think at this point, I can tell you 2 magic tricks that you can do with sheaves. And maybe I'll stop there. I can outline the rest of it. So let me, just to make it easier to draw. Imagine, and we're not doing this, but just imagine, just for simplicity, that we have a graph Y and we have a graph V. Let's just say that G is the graph, and let's forget about the red for now. And let's say Y is like this. The reduced Betty number of this is 0, this is 0. Even if we talk about the Betty numbers, the Betty number of this is 1. The reduced Betty number is 0. The real Betty number is 1. This reduced Betty number is 0. It's Betty number. It's certainly true that if we take the translates under G, so now I'll say in Z mod 3, just to be concrete, of Y. And we compare this, let's say we compare this with 2 copies. That whatever Betty number we want, reduced or not, first Betty number is less than or equal to this. Now, really, what I want to do is, I probably want to,
But you mean GY or?
yeah, GY, thanks. Here, what I really want to do is probably, if you want, maybe I want to have this to be a bicolored graph, so I'll put this. When I bicolor the graph, the reduced Betty number of this is 3. The Betty number of this, without reducing, is 4. Of this is, if a tree, we have the reduced Betty number of this is 2. I'm not gonna look at the first Betty number. And then if you take the reduced Betty number of this graph, y with the loops, we get 2. So to prove this inequality is the same thing as to prove that, so now maybe I'll add all of these, but it's going to be hard to draw. But if we take 2 copies of the entire graph G, then we want to prove this inequality, basically. So this is the right-hand side, the left-hand side, and this is just, we take the Betty number of G and the reduced Betty number Y is 2. So we want to prove this kind of inequality. I mean, I should really add all of these loops. Let's say we want to prove this inequality.
This is a tautology, right? It's just a restatement of the inequality.
Just a restatement, yeah.
And the number of copies of G you take is exactly D1 of Y, right? D1 of
Yeah,
Y.
yeah. So I'm gonna take, in general, for general Y, I would take B1 reduced Y copies of the graph G. Let's say I want to prove this. Here's a terrific idea that completely fails. There's a theorem that if you have a surjection G1 to G2, then there are inequalities with the Betty numbers. Then BI and BI prime for G1 are less than the same for G2. So let's take a surjection of this graph onto this graph, and then we've proven the Hanna Neumann conjecture. It's a pretty short proof. So what we want to do is so we're going to take this graph and translate it. So it's going to be this graph, and then translate it. This edge is over here. And we'll take the direct sum of 2 copies. And we'll take a surjection of graphs, and then we're done. Unfortunately, there's no surjection. If you map these 3 graphs as graph morphisms, you have to map maybe 2 to one of them and 1 to the other. And as soon as you map, say, these as graphs here, and this to here, it's not surjective. The single arrow, the single morphism from this graph to here is not surjective.
But what do you assume about G1? Is this an immersion or? No, in the uppermost.
This is, I mean, what I'm really assuming here is that there's really some graph G here, and you have a map here, and maybe these have to be a tau. There's some conditions
Okay.
under which this is true. But if you represent these as sheaves, then there is a surjection. So there's like two sheaf magic tricks, which is as sheaves,
Could you perhaps produce a definition?
there is.
I was wondering the same thing, if anything. Sheaves.
Okay, so as sheaves, there's surjection, and two, once you go through this really painful proof about having a surjection of sheaves, then the whole conjecture is immediately implied.
What is a sheaf in this context?
Okay, there's a short answer and there's a longer answer. So the short answer is you make a topological space where the open subsets, you start with a graph with vertices and edges, and you look at all open subsets which are declared to be all subgraphs. If you have a graph G, you can associate that to a vertex set and an edge set. These are just the disjoint union of vertices and edges. If you say an open subset, we call this X, open subset of X is just the subgraphs. We have a subgraph G, and the open subset is just the vertices of G. Disjoint union of the vertices of the edges of G prime.
So it can be any subgraph, not necessarily like a connected one or something?
That's right, any subgraph. But it does have to be a subgraph. And a lot of people have given me a lot of grief for calling this open and not closed. Because the usual way that you think about it, it's like, a point is a point. It's like a closed thing. And then an edge with the 2 points is a closed thing. But because of the way this is stated, for me, it's easier to think this way. Now, and then we just take sheaves on this. Then I take a sheaf of F vector spaces on this topological space. So, what a sheaf is on a topological space, you're done. Fortunately, you can be much more concrete. So it turns out, for a finite topological space, you can look at the open irreducibles. This is a subset of all the open sets. You could probably guess what an open irreducible is. It's one that can't be broken up into two more opens. And to talk about a sheaf on the finite topological space is enough to look at a pre-sheaf on the open irreducibles. So what this means is you have vertices. Essentially, you have the edges. These are some dots. These are edges. Maybe this is UVW, this is UV, this is VW, and so on. You have open inclusions. And the sheaf gets a vector space for each edge and for each vertex, and it maps from the vertex, the edge space to the vertex space. So if
We could think of this as the definition. right?
think of this as the definition, if you don't want to
For every
bother.
edge, we have a vector space, for
Yeah.
every vertex, we have a vector space.
So a sheaf, a vertex space of F vector spaces on G is by definition, it's F that consists of the following data. So for each vertex, there is a vector space. FV is a vector space. For each edge, you have vector space. The way I've defined it here, it means that there's connecting maps from the spaces on the edges to those on the vertices, and because of the way I did it here, it means that the maps go from the edges to the vertices. So for every edge, there's a heads map at E, which goes from the vector space on E to the vector space on the head of E. And there's a tails map that goes from the edge space on E to the tail of E. So because the inclusions go this way, the maps of vector spaces goes the other way. And now you can talk about,
These are linear maps?
these are linear maps, yeah. This is what the data is. And now you can talk about, you can talk about, what is the reduced first Betti number of a sheaf? This is a slightly more involved definition. But more importantly, you can find a surjection in graph theory for the sheaves associated, where there isn't one for the graph. So if, say, G is, let's say, a triangle, and we'll ignore any red edges, then, in other words, if this is, V1, V2, V3, and this is V1, V2, V3, there's sort of the simplest sheaf in the world is the one where you have F at each edge, F at each vertex, and the restriction maps are just the identity. You can then talk about, say, the edge space, which is the direct sum of all the edges. And you can talk about the vertex space. And then there's a well-defined incidence matrix. From the edge space to the vertex space. And it's like the usual incidence matrix. If these were all just one-dimensional, you'd have a head, and you'd have a tail, you'd have a plus, and you'd have a minus. And so you can define, say, a map D where D is really, it comes from a heads map minus the tails map. And the heads map just takes, for every piece in here, it takes the tail and it maps it into the tail space here. And for every head, for each edge and its heads somewhere in here, you take that restriction map. So these are usually called restriction maps. And then you have to get used to the way morphisms work in this context. But the claim is that there really is surjection.
Joe, we're already past 12:30, so.
Oh, okay, yeah. I could go on for another 3 hours, probably like that.
Can you say how the sheaves help you avoid the problem with the surjection that we had?
Yeah, so basically, if you think of like this, trying to map the two copies here. If you represent these as sheaves, you'll basically take the sheaf that is constant on the vertices and the edges but you'll put in a 0 here. And you'll do the same. You'll have a 0 here in the constant, and you'll do the same with 0 here. Now the sum of these two sheaves
2 dimension.
is 2-dimensional, yeah. So you have an F2, an F2, an F2 everywhere
With the identity maps.
with identity maps everywhere. And now, when you get used to these, you see, what does this mean? It means that you take, say, 1 to some element alpha.
If we on the vertices?
Right, so when you take,
Now surjection that you mentioned will be at least 2.
so on all the vertices, there's a 3-dimensional space. On all the edges, there's a 2-dimensional space. But the maps are sort of twisting around. They're not, they're, these two map to the identity and this maps to 0. So the sum of these is some kind of thing where you have F3 on all the vertices. You have essentially an F2, but the inclusions are a little bit different. So because you have F3s and F2s, there might exist this surjection. And if you take, 1 goes to alpha, 1 goes to beta, 1 goes to, let's say, 1, 0, and 1 goes to 0, 1, you have 1 maps to 1, 1. Then, because any two of these are linearly independent, you get a surjection. Now, if you want to in graph theory, you can say, well, we have fractional graphs, like maybe I map this to half of that. Fine. If you're comfortable with that, fine, you can do that. But you don't get inequalities out of this thing. In sheaf theory, you do. This becomes a short exact sequence then of some sheaf here, some other sheaf, and you get some kernel. And then to prove an inequality about the Betty number, first Betty number here and here, or the reduced Betty number, it's enough to look at this. Now, that doesn't solve your problem completely, but it shows you where to look. In this, it's by studying this and what these maps will look like, you get a solution. And if I had another 15 minutes, I could say a little bit more about it.
For lunch.
Yeah. Anyway, thanks for all your attention.
So maybe we have time for a question or two if someone wants to ask.
When does the like lunch closes here at 1 or something?
At 1:30.
1:30, okay, so I won't make you miss, okay. I would feel really badly if everyone here was to go hungry till dinner time.
I have a feeling like these techniques are useful for, what's the kind of scope of these
Okay,
techniques
so
for other problems?
there are other people who've introduced sheaves over the years, some more recently, to model other kinds of things. I've seen 1 or 2 papers in some sort of, machine learning type thing, where you have a graph and you want to model something, but with 1-dimensional spaces on each edge and vertex, you can't really model it. But if you make it slightly more than 1-dimensional, then you can. There are other ways that people use sheaves, but the way that sheaves are used right now, it's very different for the different people who use them.
So one nice thing is that these expander codes can be viewed as sheaves on you put like little codes on the vertices and the connection maps tell you how they need to be consistent, and you get a code
Does this kind of topological, I mean, here, they're usually really using topological way, right? Because giving you inequalities between the vector which have to do with the topology.
Yeah,
They're giving you
yeah.
something new about code.
Well,
This
this
viewpoint?
maybe can, the Betty numbers are dimensions of some quotient spaces, so it can give you the dimension of the code, for example. So quantum codes really look at these things. Those dimensions are the dimension of the code.
So you should tell me more about this.
Yeah, I have. Okay, no more questions. Well, thank you very much.